Hi everyone. This video is the solution to example 3 on the topic of complex stress. The idea behind this video is to find the direct and the shear stress in any inclined plane that we want. In this particular example, we're trying to understand what happens when the square rotates 30 degrees, and we're going to try to figure out what is the axial stress and what is the shear stress that we see in this inclined plane. So the way to do this is first we isolate the triangle we're trying to calculate. So I'm going to draw this triangle here. So I'm going to etch it for the video. And I'm going to call this A, B, and C. And we know that there's going to be a 90-degree angle there at C. Next thing we're going to do is draw our forces. I'm going to draw the 80 here and the 30 here. I'm going to draw it like this because I need a little bit of space between them. And I also have a 30 in this direction, as well as a 35 that was the axial force in the y direction. And now what we're trying to do is to find the stress sigma and the stress tau that will make this triangle in equilibrium. So one of the first things we need to understand in this problem is that so far we've been talking about a triangle that doesn't have a thickness, because the thickness is not very important for the problems that we learned how to solve previously. But now that we're talking about stresses and we're going to find the equilibrium inside this square, we need to transform these stresses. So all of these are stresses, this red, and we need to transform them into forces. And the way to transform stresses into forces is to multiply by the area. So the way to solve for sigma is to try to use the sum of forces in the direction of sigma equals to 0. So one of the things we can find out between these two forces, so tau and the sigma, is that they're perpendicular. So if we study only this direction, so the direction parallel to sigma, the force tau will disappear, and then we'll have one equation to find sigma. So this is going to be our main equation. So the first thing we need to do is sigma that we're trying to find out. It needs to be multiplied by the side AB, and needs to be multiplied by the thickness T, so that it gives us a force. Again, if we take that sigma, and we know that sigma is being applied in AB, and also it has a thickness T, so I'm going to draw what this T is. Is this thickness here or here? We're going to be able to find the force that is generated by that stress. So that's one thing. And now we need to start adding or subtracting all the other forces in this figure. So one thing I'm going to do is look at this 80 and understand that the 80 is going to have a component that looks like this, that is opposite of the direction that I assumed for sigma. So what I'm going to do next is minus 80. And now 80 is acting at side BC, also needs the thickness T, but now the 80 needs also to account for this angle here, so I get that component. To find that angle, I usually try to do a very nice drawing, so then I don't have to think too much about that particular angle. So I know that this angle here is 30, so I'm going to know that this angle here is 60. Then if I measure the perpendicular over there, then I know this angle here is also 30, and then I know that angle here is 60. And I'm going to do this for all my angles, so then I don't have to think too much about what is the angle I need to use to apply my cosine. So this is going to be 60, that is going to be 30, and now finally this one is 60. Now that I've done that drawing, I can easily identify that this angle here in the 80 is equal to 30 because it's the same as this angle here. So now I know if I want to find that component, I'm going to multiply this by the cosine of 30 degrees. And this is it. So now I'm going to repeat this for all the other forces, paying attention as well to the direction that the force has in this sigma direction that I'm assuming. So I can see this 30 is going to be positive, something that looks like this. So the next one is plus 30 times the side BC times thickness, and now that angle over there is the same as this one here, so it will be cosine of 60. Next one is that 35, so the 35 will have a component that is negative as well, and I can do the 30 as well. The 30 should be positive in that direction, So I know it's going to be minus 35 times AC times T times, and now that angle over there is 60, so cosine of 60. And then finally is plus 30 times AC times T times, and now that final angle is cosine of 30, as it is the same as that one over there. This needs to be equal to 0. So we already understood that the thickness won't be important for this equation, but we need to consider it as to always remember that we're doing an equilibrium of forces and not an equilibrium of stresses. So the next thing we need to do is rewrite all of these dimensions according to the same variable. So one thing we can do is, looking at the triangle, we know that the cosine of 30, if we know that the cosine is the adjacent divided by hypotenuse, the hypotenuse is AB, and we know the adjacent of this angle of 30 is that side over there, so it's the side BC. So we can say that BC is nothing more than AB times cosine of 30. Now, if we now try to do the sine of 30, we know this is going to be equal to the opposite divided by the hypotenuse. So the opposite is AC, and the hypotenuse is AB. So we do the same trick. The AB goes to this side, and now we know a way to replace all these BCs and ACs with an expression that has AB. So what I'm trying to do now is rewrite this big expression, substituting BC and AC by AB cosine of 30 or AB sine of 30. So what we get is sigma AB, that stays the same, minus 80 times AB times cosine of 30. And now there is a cosine of 30 there as well, so we need another one. Now we need plus 30, and now we're going to replace BC by AB cosine of 30, and now the cosine of 60 stays there. Then we need minus 35, and now the AC is going to be replaced with sine of 30 AB, so AB sine of 30, and then there's a cosine of 60. And here, obviously, you could write that the cosine of 60 and the sine of 30 are the same. And now plus 30 times AB sine of 30, and now cosine of 30. And again, this is equal to 0. So we managed to get rid of AB in this way, and now we have one equation to find the variable sigma. So now what I'm going to do is calculate all of this, put all of this in the calculator, and then I'm going to send it to the other side of the equation, so I'm going to change the sign. If I do this, I'm going to get minus 42.8, so I'm going to change it to the other side, and it becomes plus 42.8 Newton per millimeter squared. And now, since it's positive, the direction I assumed in the beginning, so this sigma direction, is the one that stays. So I know that this will be in tension and will be looking like that. So I know that this value here is going to be 42.8. So now that we found the value of sigma, we need to repeat this calculation to find the value of tau. So I'm going to draw my triangle again and draw my forces. So I have the 80, then I have 35 like this, then I have the 30 like that, and another 30 like that. I know I have my A, B, and C, and I know I have my thickness T as well, so I'm going to draw it as well here. And now what I'm trying to do is repeat the calculation to find the value of the shear. So it's a very similar process, but now we need to do the sum of forces in the tau direction. So we're going to do the sum of forces in this direction, because we know it's the one that will cancel the sigma that we just calculated. So this equation here can be rewritten as, so the first thing is tau times AB times thickness, and now the 80 is going to be in that direction, so it's going to be negative. The 30 is going to be positive, so it's going to be like that. The 35 is also positive, it's the same as the 30, and then that 30 over there is also going to be positive in that direction. So what we're going to get is minus 80 times something, plus 30 times something, plus 35 times something, and then 30 times something. Now we're going to write down the sides. So this is BC, and this is also BC, and this is AC, and this is AC. We know that we need all the thicknesses. That is going to simplify in the next step. And now we just need to look at the angles. That angle over there, so I'm going to copy the drawing I've done from before. And now that I have all my angles here, I know the 80 is going to be cosine of 60. The 30 will be the cosine of 30, so that's the one inside the triangle. Then the 35 is the same. And then the last 30 is this angle here, so it's also cosine of 60. And at the end, this is to be equal to 0. Now we can simplify the thickness. And now the next thing to do is to replace BC and AC with the respective AB times a trigonometric ratio. So we know that BC is with a cosine. So let's try to do this. So we're going to get that sigma AB minus 80 AB. And now this is with a cosine. Cosine of 30, cosine of 60. Now plus 30 AB. This is also cosine of 30. And then we have another cosine of 30 that we already had. Then we have plus and plus 35, 30. The AB is shared between the two of them. Now this one becomes sine of 30 and sine of 30. And now we had already a cosine of 30 here and a cosine of 60 there. This is equal to 0. Now we're in a position to get rid of all the ABs, and now we should be able to put all of this in the calculator and then change the sign to get, send it to the other side and to get the final answer. So we know that sigma equals, so now I'm going to put this in the calculator. Okay, so I noticed a mistake here in my calculation that was done right from the beginning. So this arrow here of 30 should be pointing upwards. So it should look like this, which means that the component is going to have that direction, which should be negative. So this component here should have been negative, and the angle is still 30. So this angle here is the same as that angle there. So now I can change this to a minus sign, and now I should be able to have the correct answer. So let's go to the calculator again. So if I take this in the calculator, I get minus 34.5. So I send it to the other side, it becomes plus 34.5 Newton per millimeter square. And again, the direction, since it's positive, is the same that it's assumed in the beginning of the problem. So we're going to assume that this shear has this direction, so it's positive. So we know that this value here, so again, when we rotate this 30 degrees, this value here is 34.5. There is also a little issue with this video that I told you we were calculating this face here when we rotated the 30 degrees, but we're actually not calculating this face, but we're calculating the opposite face. So the 42.8 should be measured over here. So 42.8 is correct in both cases, but the tau, so the shear force, is actually not correct. So we just calculated this one on that face over there, so on the opposite face, and we calculated that is equal to 34.5 in that direction. So the 34.5 is correct in this case, which means in the other face we get facing it upwards, so tau is equal to 34.5. Now, one final thing to discuss with you is we learned what happens if we rotate, and again, let's remember that if we take our square like this and we rotate it 30 degrees from the original horizontal position, we get this square right here, but we can also find this in the Mohr circle. So the 42.8 and then the minus 34.5. So if we take this side here, we know that this in the Mohr circle will be sigma equals to 42.8 tension, and then the tau, based on the conventions, this will be minus 34.5. And remember that we're applying a rotation of 30. So if we go to the Mohr circle, and let's go there very quickly, and if we remember that the Mohr circle, all the rotations are measured times 2. If we take here from point A and we rotate 2 theta, so if we rotate it 60 degrees, remember we're applying 30, but here we need to multiply by 2. This point we just calculated here, let's call this point X, is the one we just calculated that has a sigma of 42.8 and then a tau of minus 34.5. So this concludes this series of videos. We learned how to calculate the stresses using equations. We learned how to calculate using the Mohr circle, and also we learned how to calculate using equilibrium equations. But to show you that all of this is coherent and it falls under the same umbrella of complex stress. So thank you for watching and have a nice day.